All right, let me get the chat window open. All right, hi, everybody. Good to see you again. Oh, these faces. Hi, Ryan. Hi, Stephen. Hi, Sarah. So, oh, here comes Abdullah. Okay, so here it is. None of us thought we would ever make it to this day, but here we are, the very final day of Calc 3. And, you know, it's obviously a sad day for all of us, but, you know, we're going to get through it somehow. So let's talk about some admin stuff first. So first of all, you know, you've gotten information probably from the university about course evaluations, and I think today's the last day to do them. And a lot of you have already done it, like half the class, I think, had already done it last time I checked. So that's awesome. They would like for, and I would like for more participation. So we're going to have a little bit of time at the end of class, a little bit of extra time so you can take just like we sort of do if it was in person. Also, just a reminder, I am going to have an extra 3 hours of time that I'll just be hanging out, ready to answer questions. So I'd like to treat it, rather than office hours, I'd like to treat it like a problems, like a study session or something like that, where you guys just are there studying and working together, and I'm there in case there's any questions. But don't show up. I mean, you don't have to have questions before you show up. Show up to just do problems, and questions might generate themselves. And if you want to show up with your partner, then I can put you both in the same like breakout room, and you can practice working together on problems, and then still if questions come up, you can come find me, I'll come help you, that sort of thing. So I hope that will be helpful. And even though I picked the same time as our normal meeting time, I don't think anyone has classes on Thursday. And if you want to come to the whole thing, you can. Come to all 3 hours. That's totally fine. I'll be there. I hope somebody shows up. And those are my announcements. What questions does anybody have before we start doing some math? Nothing. I know you just want to get to the math. I know how you feel. Let's do 13.9. Let's let in Adrian first. Okay, section 13.9 says this. It's the divergence theorem. The divergence theorem is such a cool theorem. It makes so much sense, and it connects all these things together that we've been talking about in various ways for the last month or so. And it's just really satisfying. And not only that, it takes a reasonably complicated computation and turns it into a sweet, easy little computation. And who doesn't like that? So let's get in there. Here's a divergence theorem in space. It's a three-dimensional thing only. So, well, there's a version in 2 dimensions, but we're not going to talk about it. So divergence theorem in space. So like any good theorem, there's conditions for this theorem, and I'm just going to start right out with these. So let's suppose we have, first of all, well, I said it has to be in 3 dimensions, so the vector field is 3-dimensional, so F is a 3D vector field. Then we also need a surface S that is closed. Okay, so S is a closed surface. I haven't told you what that means yet, or before ever, but closed means there's no boundary, there's no holes. It closes something off. So remember when we talked about a simple closed curve, the cool thing about having a simple closed curve is since it closed off, that meant there was an inside and an outside. That's the same thing with the closed surface. A closed surface will have an inside and an outside. So let's see, so let me just write this down. A closed surface is has no boundary and no holes. So a good example, a sort of standard example of a closed surface is a sphere. A sphere is, it's all closed up. There's the inside, which is the ball, and there's the outside, which is the other part of it. And you can't get from the inside to the outside without passing through the sphere. There's no sort of secret way out. So it's all closed up. So S has to be a closed surface. Then you also need outward orientation for S. And then this last thing isn't really a condition as much as it is sort of just naming. Since I'm talking about, since I'm saying that S closed means there's a region on the inside, we're going to name that region on the inside, just call it W. It's a 3D region inside of S. Okay, so if we have all those conditions, then here's what's true. Well, okay, left-hand side. Let's think about what this might mean. The triple integral of the divergence of F dV all over the region W. So let's see, I've got some closed surface S. I don't know what it looks like. It's maybe some sort of blobby thing. And that's S is the boundary. And then the region W, that's on the inside. Or I could write it W and then put the arrow like this to show I mean the stuff inside and not on the edge. So tell me, what does the divergence of a vector field, what does that measure? Divergence. Who remembers?
Is it like the magnitude of a vector expanding or like contracting?
It is a measurement of the amount that the vector field's expanding or contracting at a point. And but it's actually a scalar. And so you did say it was a magnitude, so it is a number. That's right, it's a number which measures the amount of expanding or contracting. And some places maybe there's expanding, and some places maybe there's contracting. So like maybe over here, there's some expanding going on, and I mean this to look like it's a point inside W somehow. And then maybe over here, there's some contracting going on. And over here, there's more expanding, I don't know. Different things can happen at different places. And the divergence is a number which indicates the rate of expansion at a given point. If I integrate that dV, integrating just means adding up. So I'm really just adding up all the divergence. I'm accumulating the divergence all over the region W. So I'm accumulating the amount of expansion of the vector field all over the region W. So I can just say this is accumulated. This will be a little bit vaguely worded, but amount of expansion of F throughout the region W. Accumulated amount of expansion. Okay, so another way that my advisor explained it to me, actually, I kind of liked this idea. Like, imagine that all of space, there's some places in space that are, gas producing factories. And so this one's a little gas producing factory. This is a gas producing factory. And it's, as it produces gas, the gas emanates out from these sources and expands. And then I guess that would make these places here gas sucking factories, gas destroying factories, where they're just going to pull it in and kill some of it. And if I add up the divergence all over the region W, what I'm getting is the net amount of gas being produced, which is sort of the same as the net expansion of the vector field. So if there's overall more positive divergence than negative divergence, that means that we're producing more than we're destroying. Where's that extra going to go? All through this region, it's more is being produced, it's being destroyed. So there's some extra. What's going to happen to it? What would happen in real life? Could that just keep going on forever? You just keep producing more and more and more and more gas? No, it'd be weird.
You're saying the region would expand?
Yeah, either the region would expand. That's a good answer for the physical situation. If I imagine that S, instead of actually being a physical surface, it's just a mental surface, like this is a marker of here's the region we're talking about, but it's not built out of anything physical, it's just sort of a location, then what's going to happen? Where's it going to go? Where's this all this extra gas going to go? Well, it's going to have to go out through the surface. It's going to have to pass outward through the surface. What's that called? When we measure how much the vector field's going out through the surface.
The flux?
That's the flux, exactly right. So the amount of divergence all over the inside is same as the outward flux. That's what the divergence theorem says. So, Philip just figured out the divergence theorem all on his own. There's a little bit of things to prove. I'm sure he'll get back to us in a few minutes with that proof. But the idea is the idea makes sense. It's going to be the outward flux. This is sort of outward flux, or the amount of the vector field, how much is passing through the boundary. Okay, that's what the divergence theorem says. And yeah, personal favorite. Okay, let's just try an example. Well, and does anyone have questions about what I've written so far before I get to an example? Okay, let's try an example. Okay, so let's say S is the cylinder of radius 2. Height 2. My cat's sitting on my notes, so I don't know what the function is. And centered at the origin with lids. And F is the vector field xy squared, x squared y, x squared e to the xy. What is the flux of F outward across S? All right, you know that I'm gonna, sorry. Yes, okay. Sarah asked a question and I didn't notice it because I had stuff hidden. So you know that we're probably gonna use a divergence theorem since I just told you, let's do an example using the divergence theorem. But also you want some intuition of why you would use the divergence theorem if nobody was hanging over your head saying, hey, this is the theorem that you should use. So let's first think about what would it look like if we tried to do this directly. So first try directly. First think about it directly. Directly means not using a theorem. Okay, so what do I have? I have this surface. It's a cylinder, radius 2, height 2. Centered at the origin. That's the surface with lid, so it includes the top and the bottom and then also the sides. There's our surface. If I want to do this directly, how do I, it's a surface integral. What are the steps? What do I need to do in order to evaluate a surface integral? What's the first thing? That's always the easy answer. What's the first thing we always do?
Parameterize.
Parameterize, absolutely. So first we would parameterize. Well, how many things would we have to parameterize?
2.
Well, even worse, 3.
Well, you just parameterized one lid, right? Or do you have to do both?
You have to do both because they're in different locations. So we're not necessarily just finding the area, we're finding out what the vector field's doing at these different locations. So yeah, so we'd actually have to parameterize 3 things. You have to parameterize top lid, the side, and the bottom lid. So that would be parameterize 3 surfaces. And remember, after we parameterize, what do we do next?
Check orientation.
Yeah, well, we want to check the orientation, absolutely. And to get there, we have to do the RU cross RV to figure out what the orientation is. So that would have to come first. But yeah, that's going to be needed. So we're going to calculate the RU cross RV for all 3. And then check the orientation for all 3. And then now we can do 3 surface integrals and add them up. I think that you can do this, and probably for practice, whenever you're practicing for the exam 4, it might make sense for you to just try this. Just see, can I do it the long way? They're just 3 surface integrals. But when I say just 3 surface integrals, I mean just in the sense that it's not beyond you, but not just in the sense that, I mean, it's definitely going to be a lot of work. It's just work that you can do, but maybe we can make our lives easier. So that's how it'd be directly. And I'll just say this looks like a lot of work. Okay, so instead, let's try to use the divergence theorem. So what about the divergence theorem? Instead, use the divergence theorem. So, well, if you use the theorem, what do we have to do in order to use the theorem? What are the pieces we have to include in our problem?
Conditions.
We have to check the conditions, absolutely. So we already named it, that's good, and we have to check the conditions. So check the conditions. Okay, first of all, needed a 3D vector field. Okay, well, we've got that. Look, here's our vector field right here. It's got 3 components. We're fine. So I'm just going to say I looked at it. So F is a 3D vector field. Yep. I need S to be a closed surface. Is that true? Is there an inside and an outside, or is there a way to sneak from the inside to the outside without passing through S? No, that's right. It's good. It's closed. Okay. It's closed because it's got the lids. If it didn't have the top and the bottom lids, then it was just the side, then it wouldn't be closed because I could be what you might think of as inside and I could just sort of crawl up and be outside. So yes, because S includes lids. Outward orientation. Well, let's see. The problem asks for outward flux, so that's good. And then Last thing, well, we need a W to be the inside. We don't have a W. We don't have a name for the inside. The point is we just need a name for it. So let's just call it W. Okay. And if we do that, remember, I still want to start with what's being asked. We were asked about the flux, and I want to answer something about the flux. I don't want to start with the triple integral if I'm being asked for a flux. Okay, so we're going to start there, but we are going to use a divergence theorem. So we'll end up swapping this surface integral for this triple integral. And when we do, we realize, oh, we have to calculate the divergence in there. So let's just calculate the divergence first before we start into the calculation. So calculate the divergence of F. Oops, I didn't want to. Let's see, the divergence F, that's the del operator dotted with F. So partial with respect to X, with respect to Y, with respect to Z, dotted with, well, what's F again? F is xy squared, x squared y, x squared e to the xy. So remember, we're doing the dot product, so I've got partial with respect to x of xy squared plus partial with respect to y of x squared y plus partial with respect to z of x squared e to the xy. Let's see, with respect to x of xy squared, that's just y squared. With respect to y of x squared y, that's just x squared. And with respect to z of x squared e to x, that's 0 because there's no z's in there at all. Okay, so there's our divergence. Okay. So now we're in a position where we can calculate the outward flux. I'm going to leave a little bit of space, and maybe you'll see why in a second. So calculate outward flux. Okay, so well, the double integral f dot ds is equal to, by the divergence theorem, the triple integral over the inside of the divergence of f dv. Remember, when we're doing dv, or when we're doing any of these problems, we have to choose coordinates, choose a parameterization, choose coordinates, so on. What coordinates make sense for our region? What do you think?
Can we use cylindrical?
Yeah, that's right. Good idea. Cylindrical are going to be the right coordinates to use for this. So, so we're going to write all this in terms of cylindrical coordinates. And remember, since we used a theorem here, here's what I'm going to say by divergence theorem. This is the line that we used it in. Now everybody wants to be in terms of cylindrical coordinates. So I'm going to go back. I need the divergence of f in cylindrical coordinates. So that's why I left a little bit of space here, because let's just go ahead and put this in cylindrical coordinates. What's that going to be like? What's x squared plus y squared in cylindrical?
Is that r squared?
Yeah, it's r squared. Good. You might think, and you'd be right, that it's r squared sine squared theta plus r squared cosine squared theta, and then you combine it all together, and it's r squared. But we've already seen also sort of that's like the definition of r comes from the Pythagorean theorem. So yeah, this is just r squared. Okay, so the divergence of f is just going to be r squared. And then dv, if I'm using cylindrical coordinates, dv, what's that? What did I put for dv?
Is it r dr d theta dz?
Exactly. Thank you. I was hoping that that somebody would remember that there's an r, dr d theta dz. And we might worry about what order to put the r and the theta and the z in, except when we look at this, you realize, oh, actually, hey, everybody's bounded by constants. So r is the radius 2, so r is between 0 and 2. Theta is between 0 and 2 pi. And z, well, it was height 2, but centered at the origin. So it's going to be from -1 to 1. Okay, since they're all constants, it doesn't matter what order we do them in. So we've got r first. So r goes from 0 to 2, and then theta first, 0 to 2 pi, and then z first, -1 to 1. Okay, this one, I'm not going to finish this problem because I know that you can do this. This one's an easy antiderivative. I know you got this one. I'd rather spend time on new, more challenging things. But look how easy this was compared to what we might have faced with parameterizing all three surfaces, doing the partial derivatives, taking the cross products, checking all three orientations. So the divergence theorem saved the day. So yay for the divergence theorem. This has turned into an easy integral. So I guess Aima did the right thing, which I'm so happy about. I wanted to point out that the dv, you have to put in your own, you know, whatever scalar fudge factor that we have for converting from one set of coordinates to another. Whereas the ds, this sort of had that built into it. You didn't want to add an extra r or an extra rho squared sine phi if you happen to be using coordinates similar to cylindrical or similar to spherical. Okay, so you needed to add, don't forget to add this in the dv. And we didn't, so that's good. All right. Any questions?
Is it just for dv and dA that you need to add in like the extra factors?
Absolutely. And then the ds and the dr, that all takes care of itself. Yeah. So maybe it's worth saying here, do not need to add these sort of extra factors. Because it's built in. Only you must add it for the dv. All right. What do you think? You want to try one on your own? Steven's like, heck yeah. All right, let's do that. How about, this one will be interesting. Let's go straight to this classwork problem. So let's find the flux of f equals x cubed, y cubed, z cubed, inward across the unit sphere. So I'm going to give you about 5 minutes to think about this, work on it, and then once you've got your head around it a little bit, then I'll help you talk about it a little bit. So take a minute to see what you can do. Okay, let's talk about this for a second, just to make sure we're all on the same page before you get into a computation too heavily. Okay, so you probably have a sense that we're going to use the divergence theorem since this is the section we're in, but let's try to figure out why it makes sense. So we want to think about the conditions. That's a 3D vector field, that's good. What about S? Is S closed? Yeah, that's right. There's an inside and an outside. There's no holes. There's no boundary. S is closed. Okay, so that's good. So let me just check these off. 3D, yes. Closed, yes. Outward orientation? No. Crumb. Does that mean we can't use the divergence theorem? Divergence theorem needs outward orientation. What do you think?
We just put a negative.
Yeah, that's right. So the inward flux is going to be the negative of the outward flux. So, but let's not lie about it. Let's, rather than just not check it and hide it and stick a negative, we're going to just come out and say, hey, nope, we don't have outward orientation. So we want problem asks for inward. We're going to use the divergence theorem to find outward flux, and then make it, and then the negative of that is inward flux. So I guess if I were trying to be tidy about things, I'd be like, oh, well, I didn't really have room for this. I'm going to put, oops, I didn't mean to move that X. Fix. Oh, I can't move it. Okay, I'll wait by him in a minute. Oops. So many problems. I'm going to figure out how to use Notability just in time for class to be over. Okay. And let W be the region inside S, so that's fine. Okay, so we sort of have all the conditions. Let me show you how, maybe you've already set it up, maybe you've already finished it, but let's talk about how we would set up this problem. So what's the next thing we should do? Did anybody try?
Calculate divergence.
Yeah, calculate the divergence, good. So let's see, partial with respect to x of x cubed is 3x squared. Partial with respect to y of y cubed is 3y squared. Partial with respect to z of z cubed is 3z squared. Okay, so did anybody get the divergence theorem? Did anybody get the setup yet? Or do you need a little more time? Who would like a minute more time to set things up? Yes, okay, I'll give you like a couple more minutes. Okay, so let's see the inward flux. Oops, that should be a capital S. Is negative of the outward flux. And it's the outward flux that we can use the divergence theorem on. What coordinates should we use? Did anybody choose coordinates yet? What makes sense? Oh yeah, Stephen just wrote spherical, absolutely. So we use spherical coordinates. So if we do that, how do we convert, what's x squared plus y squared plus z squared?
Is it just rho squared?
Yeah, it's just
So
rho
it'd be 3
squared.
rho squared.
Thank you, 3 rho squared. Okay, so that's the divergence. So what about dv?
We know dv is just rho squared and then sine phi, and then
Thank you.
d rho d phi d theta, or whatever you want to do.
Yeah, good. Thanks, Safa. Okay, so rho squared sine phi, we don't want to forget that extra sort of multiplying factor, d rho d phi d theta. And rho, well, let's see, it's the unit sphere, I think. It's a unit sphere, so rho goes from 0 to 1. Phi goes 0 to pi. Theta goes 0 to 2 pi. I think that's I'm also going to leave this problem. I think this is something that you can do. But actually, maybe I'll give you a second to do it and make sure everybody gets the same answer. I'll try to do it too. Is that right? Yeah. All right, I get negative 12 over 5 pi. Did anybody else get that? Still working, okay. All right, we got some heads nodding. That's good. All right, so there's been a request to do one with a hyperboloid. How do you feel about that? Yeah, everyone loves hyperboloids. I can tell by the jubilance. Okay, so what if I just make something up? I don't know how horrible this will be. Let's just set it up and not evaluate it so that if I make something up and it's not easy to anti-differentiate, we won't worry about it. Okay, so let's just say calculate so here's another example. Outward flux across S, where S is the hyperboloid of one sheet. Let's see, what's the formula for a hyperboloid of one sheet? Remember, does anybody remember? Z squared minus X squared minus Y squared. Is that right? So let's think, if X is 0, Z squared minus Y squared equals 1, that's a hyperbola. If Y is 0, Z squared minus X squared is Z squared minus X squared equals 1 is hyperbola. If Z is 0, there's some places where that doesn't work. So how could I fix this? Does anybody know? Okay, maybe you don't. Let's, everything has to be negative. So if I did X squared plus Y squared minus Z squared. If Z is 0, X squared plus Y squared equals 1, or else it gets bigger depending on what Z is. And so I have circles, I always have circles for cross sections. And then if X is 0, then I have hyperbolas. If Y is 0, I have hyperbolas. So that's gonna be hyperboloid of one sheet. And if I have this for the vector field, I don't know, just make something up. Can I use the divergence theorem? Philip's shaking his head no. Why not, Philip? Why not, Amen?
I don't think it's closed, right?
Yeah, that's right. Absolutely. It's not closed. So if I wanted to come up with a problem where we could use a divergence theorem, I'd have to also add some lids. So let's bound it to hyperboloid of one sheet for Z between, let's say, square root of 3 and negative square root of 3. Is that what I want? Yeah. And with lids. Okay, so what would that look like? So we've got this hyperboloid of one sheet, but it only goes up so far. I guess this would be solid. And it has lids. Okay, so we've got the side to it, and the top and the bottom. Then this Z value would be positive square root of 3. And this Z value would be negative square root of 3. Okay, now good. S is closed, and we have a chance of using the theorem. Okay, so use divergence theorem. First thing, what do we do? Who knows? Are you all surging ahead and doing it? Yeah, nice. Okay. Well, don't forget, what do you always have to do if you're going to use the theorem? I just want to make sure everybody's on the right page.
Check the conditions.
Thank you. Check the conditions. Absolutely. Okay. All right. So see what you can come up with, and I'll work it along with you. 3x plus 4y. 2z. Ooh. Okay, it looks like everybody's working still. Right, who's to the place where you're ready to start calculating the outward flux? Did anybody get the calculate the divergence yet? Yeah, okay, nice. Okay, so here we are. We have to think about what we're going to use for the dv. So what makes sense for, what coordinates do we want to use? What makes sense for this problem?
I use cylindrical coordinates.
Yeah, great idea. We should use cylindrical. This is a thing with a round cross section, right? And cylindrical is the right thing for these. So excellent. So using cylindrical. Okay, so that's going to be R. Give you a minute or so, see if you can set that up, and then I'll help. How are we going to set up these bounds? In fact, maybe I don't want Z on the inside. Does anyone have them set up yet? Yeah? Okay. So I saw one nod. Let me look at the other people. Any of you guys, do you have the bound set up, or should we do it together? Together, okay. You all look so busy, I don't want to interrupt. Okay, let's think about it together. So if we want to use cylindrical, that's right. And we have some constants already for Z, so I'm going to leave Z sort of on the outside. But let's try to figure out R in terms of Z. So let's do d theta dz. So R goes where to where? So let's remember the equation of this surface was x squared plus y squared minus z squared equals 1. And if I'm going to cylindrical coordinates, that's the same thing as r squared minus z squared is 1. So in other words, r squared is 1 plus z squared. So r is plus or minus square root of 1 plus z squared. But you know what? We only want the plus because r is always positive. So when we're on the surface, we've got square root of 1 plus z squared. And when we're in the middle, we have 0. So r goes from 0 to square root of 1 plus z squared. And then theta goes 0 to 2 pi. Z goes negative square root of 3 to positive square root of 3. And we're pretty lucky because the first integral is going to make that a square, so it's going to get rid of the square root, and we don't have a trig sub after all. All right. Okay, so I'm just going to leave this. I think this is also a reasonably simple one for you to follow through with. Any questions about it? Did anyone get the answer already? Not yet. Okay, well, I'm happy to leave it like this. The hard part, I think, is like I said before, is the setting up. And from here, I think you can do the integral. All right. Oh, I wanted to say one more thing. Let's think about, I want to tie together all the theorems that we've talked about so far. So let's just think about the theorems from Calc 3. In fact, let's talk about the main theorems from calculus. Let's see, what's your favorite, what's the most important theorem from calculus?
Fundamental.
Thank you, fundamental theorem of calculus. So what did the fundamental theorem of calculus look like? Well, let's see, it was, we had the integral of f of x dx was f of b minus f of a. But there's a reason that I don't like it expressed in this version. The reason is it's not clear what capital F has to do with little f. And so it's hard to even say if this is a true or false statement if, maybe capital F isn't related at all to little f, and then this isn't possibly true. So what is the implied relationship between big F and little f? What's big F have to do with little f?
Little f is the derivative of big F.
Yeah, little f is a derivative of big F. So I'm just going to rewrite it that way. So it's the derivative of big F. And I'm also going to try to phrase this in terms of things that we've seen in more recent theorems, in terms of like regions and boundary of regions and so on. So let's just remember, whenever we were doing this integration, we had here was A and here was B, and then here was B, and then the region that we were integrating along was this interval right here. So let's call that interval I. And then what's the boundary of that interval? It's just those 2 points, A and B. So let's see. A and B, that's the boundary of I. Okay, and if we think in terms of orientation, how do we orient the interval? Well, x is increasing, go this direction. That's the orientation for the interval. And it may not make any sense to you, but here's remember how when we did like Stokes' theorem and Green's theorem, we had these compatible orientations? The compatible orientation for the boundary would be this one's positive and this one's negative. If you believe in all that for a second, here's a way that I'm going to rephrase the fundamental theorem of calculus using that information. So the left-hand side is just the integral over the interval I. Integrating from A to B is integrating across this interval I of the derivative. And the right-hand side is a sum of only two things. Well, integration is sort of notation for summation. So I'm going to be a little bit weird, about the notation and still use integration for just adding up two things. If I integrate over the boundary, that's just adding up two things. And what am I adding? I'm adding f of x with the sign. So I'm adding up f of b and f of a, except that f of b counts positively and f of a counts negatively. So f of a minus f of b because of this orientation. Okay, so that's just another way to express the same idea. Let's think about the fundamental theorem of line integrals. What did that say? So it said if C was a curve, parameterized by R for t between A and B, well, then what? Then the line integral, what does fundamental theorem line integral say? Who remembers? Hope somebody remembers. Line integral of what? What kind of vector field does the fundamental theorem apply to?
Conservative one.
Absolutely, conservative vector fields. So it said that the line integral of the gradient of some real valued function, line integral of this conservative vector field on the whole curve is equal to f of r of b minus f of r of a. And if I think about that, well, so I've got this curve. Here's curve C with some orientation. And the starting point right here, that's R of A, and the ending point is R of B. And if I go with the same, this counts as positive, and this counts as negative, then I can just rewrite the right-hand side as, I'm going to add up all over the boundary of C. The boundary of C only has 2 points, I know, but still, I'm just trying to get into this same pattern. It's going to be f of x dx. So it's going to be f at R of B minus f at R of A with the signs in it. Okay. What's another theorem we know and love? We like Stokes' theorem. Stokes' theorem says that the double integral over some region of the curl of f well, if I accumulate the curl all over the region, that propagates to a line integral around the boundary. That's a line integral of the original function f around the boundary. What about the divergence theorem? If I do a triple integral all over an entire 3D region of the divergence of f, that's the same thing as the double integral over the boundary. You see how all of these are really saying the same thing? All of these are saying things. They all look like this. The integral around some whole region of the derivative of some function is equal to the integral around the boundary of the region of the original function. They all have the same structure. Let's think about it. Why am I saying derivative of f? Well, when we started out here, the fundamental theorem of calculus, the left-hand side was the derivative of f. Fundamental theorem of line integrals, the gradient. That's a version of the derivative, right? We took the derivative with respect to x, y, and z, the partials. How's curl of f a derivative? Well, that's the del operator crossed with f, and the del operator is taking derivatives. Divergence is the del operator dotted with f. That's taking derivatives. So I'm always doing the integral of the derivative of something over the entire region. That's been the left-hand side. Then the right-hand side, we've got integrals. It's always integral over the boundary of the region of the original function. Okay. So they're all really just generalizations of the fundamental theorem of calculus through slightly different lenses. Isn't that cool that it's all tied together? I just love this so much. All right, so that's Calc 3 in a very huge nutshell. And I'm ready to take questions of any sort. Do you want to talk about the exam? Yeah, let's say a little bit about exam. So exam 4. I call it exam 4 rather than the final exam because I'm really going to treat it like the 4th exam. It's going to be just like your other exams, except on the latest material. So the latest material is going to be 13.5 through 13.9. You know, 5 measly little sections, but we know they're pretty substantial stuff here. So it's curl and divergence is in 13.5. Surface integrals is 13.6. 13.6 is just parameterization and surface area. 13.7 is surface integrals. 13.8 is Stokes, and 13.9 is divergence theorem. So that's what's going to be on there. And some people have asked, is this going to be cumulative? And the answer is kind of, because so I'm only going to ask questions from 13.5 to 13.9, but let's just think of what's involved there. So there's line integrals, which involves parameterizing. So at the parameterized curves, like we did on the very first day of class, we're going to have cross product and dot product are involved. So that's 10.3, 10.4. 10.6 is surfaces, right? Quadratic surfaces and graphing them. Then let's see, 11.3 was partial derivatives. And 11, I guess we didn't have much more of that. And then what else? There's chapter 12, which was double integrals, triple integrals, different coordinates, spherical coordinates, cylindrical coordinates. Chapter 13 had vector fields, line integrals. It's all in there, right? So it's not on purpose cumulative, except it's the beauty of this class, the way it sort of all ties everything together. The way I'm going to run the exam is be the same way we did the other exam. So I'll get there a few minutes early, and I'll make sure everybody's got their workstation set up right. And then I'll send out the exam. And then those of you who are going with partners, I'll put you in the room with your partner in like a private breakout room so you can sort of talk and work together. And I'll just be here in case there's questions. And I'll pop around to some of the breakout rooms periodically just to make sure everything's okay, if there's any questions and so on. The exam is going to be the same length as all the other exams, so meant to be an 80-minute exam. You have 120 minutes. You can take 120 minutes if you want. That's fine. I don't need to rush anything, but it's not going to be specifically longer just because there's more time. And then at the end, you'll submit it. So only one solution per pair. So if you're working alone, you submit one solution. If you're working with a pair, with a partner, then you and the partner choose and submit one solution. So ahead of time, you should decide things like who does a better job with writing up, or are you going to do something weird with where one of you writes up some of them, the other one writes up some of them, that you can somehow, I don't know how you'll do it, but get it into the same PDF file to submit, something like that. But you should come up with some way to do that. Probably is going to be easier if somebody agrees to be the scribe, and then you can sort of share what you're doing with each other. Submit one solution per pair of people, and then I will grade as quickly as I can, and that's where we'll be. You all know what grades you need to get on the final to get certain grades for your course grade. So that's all set. What else? No questions. You guys are so quiet today. Okay, I know you're so depressed that class is ending.
I just wanted to clarify one thing. On Gradescope, it says 13.9 is due, but it's not really due, right?
Not really due. Yeah, I put those on a long time ago because I wanted there to be space in case somebody was working ahead or they were on a different time zone and they were still doing problems, that they would be able to submit it. And I didn't know when, what times we would cover what topics, what days. And so I couldn't put real due dates on. So I just put them all in there. But yeah, 13.9 is never going to be due. You just do it because you want to pass the class. And I think, Stephen, did you have a question?
Yes. if we're given just like a vector field, how would we know, I guess, to use Stokes versus like divergence theorem?
Oh, that's a great question. What you should do is look to the conditions. So, like, what's the main condition you need before you can use divergence theorem?
I guess the closed part is what's
Closed
kind
part,
of.
yeah. So if you have a surface that's not closed, game over. You can't do it. Okay. And then for Stokes theorem, be careful that you're integrating the curl of something. Because if
Okay.
you're integrating the regular function, then you can't use Stokes theorem.
Okay.
Okay. That's a good question.
Cool. Thanks.
All right, well, we still have 10 minutes left, so here's what I want to do. Some of you have, thank you, some of you have already turned in your evaluations. I can't see them, but I can see the number of ones that have been turned in. It seems like you've done about half of you've turned in. That's awesome. Those of you who haven't, I'm leaving time now for you to do it. So we've got 10 minutes. That's what, if we were in person, I would hand them out to you now, but in case we're not. But if you can't find, if you don't know where that went, if you search for enterprise, that's where the link came from. I can't send you a link because everybody has a personalized link. And you know, if I had your link, I would just fill it in for you and put all the good stuff. So you need it yourself. And I don't know if you got the other email. I just sent you an email today with a link to a couple extra questions because you know, the standard USD one doesn't have any mention of going online. And this is my first time teaching online. And I've gotten some good suggestions from some of you already about ways to make it better. And it looks like I'm probably going to be online next year too, or at least next semester. And so I'd love to learn what was helpful or what wasn't very helpful or what your other teachers did that you thought would be helpful. So if you don't mind, I'd really love it if you could go to this link and add your thoughts. It's USD1 mention. Okay. If you go here and add whatever you want to add, it's anonymous. Some people have already added some, from the last class I checked, some people have already added some really constructive, interesting, and useful comments. So I'm really grateful for that. And maybe some of you will have some other things to add too. And does anyone have questions before I go? Thanks, you guys. You're a great class. You've been, yeah, thanks, you too, Philip. You've been a really good class and you've shown a lot of patience and compassion and kindness. And yeah, I'll miss you. I'll miss seeing you guys. And Steven's like, I can't wait to be done. Okay. Okay, cool. Well, thanks everybody. And I'll be here Thursday, right? For a couple hours, 3 hours. So maybe I'll see you Thursday. Otherwise, I'll for sure see you Tuesday or Thursday of next week. Good luck with everything. Bye.
Thank you.
Mm-hmm.